Thank you everyone for coming, for getting to this point in the week. This is, I think, very much the tail end, so well done everyone for surviving the extreme thunderstorms and whatever other challenges we've had this week. My name's Gary Mackenzie. I'm part of the Edge business unit. I look after some of our telco strategy pieces. I have two of my excellent colleagues here today. Tim, do you want to say hi? You need to turn your mic on for that to work, of course.
To turn my mic on. I wasn't prepared to be speaking already now. Yeah, hi, Tim Irnich. I'm the product manager for the product that you all want to hear about and that we will be talking about as well, but not only. And we have Alberto here as well.
Yeah, my name is Alberto. I'm telco engineer in the view for the Edge at SUSE.
So this is a technical session, and we will go on to technical things, but I feel the need to set sort of 2 minutes of context first, if you will bear with me. I thought I would ask a question of the room first, just to sort of date the room a little bit here, but how many people started using the internet here in the dial-up era? Okay. We're all old. I think this is all three of us. You as well? Yeah, excellent.
14.4 kilobits.
See, I remember that. Like, I'm always reminded that we said sort of 56K, and I distinctly remember I never got 56K. It was like 41 if you were having a good day. So the reason I asked this, I was sort of thinking about this a little bit last week. I was on holiday in France, and I was in the middle of rural France with my phone, getting sort of 300 meg down, roaming in the middle of nowhere. And that's sort of 25 years or so of difference, 25 years of technology moving on, of the mobile space moving on. And on one very simple level, it just makes you think technology is amazing. But the other thing it reminds me is that a conversation I had a month or two back with a big telco operator. We were talking about the greatest success of the telecoms industry and the greatest failure at the same time is that we have made magic completely mundane and everyday and routine. We're surprised when our phones don't work. And then we moan about it costing $35, $40 a month for this service that just wasn't possible not that long ago. But actually behind the scenes there's a whole bunch of stuff which makes this happen, a whole bunch of work which goes into making that service work. And actually behind the scenes, sort of the infrastructure piece, which... There are more people.
And he might not remember the dialogues.
Possibly not. No, I think we've evened out the level in the room now. I was asking everyone, like, who here started using the internet in the dial-up era? No?
No?
There we go, we're a bit more even now. So yeah, and the reason I sort of bring this up is that telco as a whole has become very routine, very mundane as far as the consumer is concerned. But behind the scenes, as we build these networks, it's still really complex. And that's sort of one of the driving factors behind what we're trying to do with SUSE ATIP, and one of the things that we aim to do in our product is make the infrastructure piece as routine as the consumer service that it provides at the end of the day. We want to make it as surprising when the infrastructure doesn't work as it is when your mobile doesn't work. So that's a little bit of context setting on the goal of sort of what we're trying to achieve with ATIP, and now we're actually going to talk about something which is actually complex, and why this is so hard. Do you want to skip on a few, Tim, and we'll talk about...
I guess we can skip this one, right? And
yeah.
Go right here.
So this presentation was originally the ATIP presentation. Discrepancy between the schedule and what we ended up putting on the slides here. But what we want to talk about today is put that in the context of a specific use case. So we're talking about radio network. Specifically here, we're going to talk about Intel FlexRAN. We'll say a little bit more about that in a second. But this is moving towards being a software-orientated solution. This is something which has always been sort of big iron hardware sitting in towers all across the country, and it's now moving towards a software-based architecture. Why are we doing this? Well, it's the same old NFV story we've been telling for a decade and a half or so. It's about flexibility It's about being able to change more easily. It's about being less locked to a specific configuration and solution. It's about disaggregation and more choice in the market as well. When you're buying big iron, big hardware from vendors, there's a limited number of people who are going to be able to do that. You get a lot of more diversity when you have it in a componentized form. We've seen sort of the first generation of NFV. This is sort of when I got involved in the telco cloud space, sort of back 2010, first iteration of Etsy NFV, when everything was virtualized, and we really just took the old boxes we had and we ran them on VMs instead of specialized hardware, and we thought we'd done a good job, but actually we didn't really get much of the flexibility that we were hoping for. Maybe didn't get all the advantages that we'd hoped for along the way. Then as Kubernetes came along, and I'm somewhat shocked recently when 10th anniversary of Kubernetes sort of came around that it's been that long, that it's that soon. But yeah, as Kubernetes came along, we moved towards containerized network functions, moving towards a more cloud-native model, moving towards hopefully getting more of the advantages we saw in this paradigm originally. So that's the sort of the why of how we got here. I'm going to maybe hand over to Tim now to talk about some of the challenges that this provides, particularly when we talk about the RAN space.
Yeah, so I mean, the RAN virtualizing or running RAN software base is probably the pinnacle of complexity, because RAN software needs to be very, very tightly performance tuned, because it needs to solve very complex equations, do very complicated computations every couple of nanoseconds, and if it doesn't get ready in time, basically, then the whole RAN stack doesn't really work anymore. So there are two key challenges related to running software-based RAN on generic compute. Number one is we need to reliably achieve performance in this generic compute environment, which, as I will allude to later on, isn't necessarily designed for such a use case in the first place. The second challenge is that this obviously leads to a relatively large amount of complex configuration that needs to be carried around. So the number of settings that you make, the number of the number of places in which you need to tune the software stack and sort of move it away from its defaults is relatively large. You end up with relatively large configuration files, and these need to be managed at scale for thousands or maybe 10,000s of instances in the field at day zero, at rollout, and along the entire life cycle. So those settings need to survive updates. You need to make sure that there is no config drift, et cetera, et cetera. So those two challenges together make up the challenge for a NFV stack that is meant to support software-based RAN stacks. So why is this difficult in the first place? The standard Linux kernel isn't designed to provide bounded response times for userland processes. So when you run a userland process, the kernel, the design principles around which the Linux kernel is designed is it can sort of the time until the computation finishes can vary within certain bounds. And there are a number of technical reasons why that is the case. I'm singling out a few of them, but there's the actual technical situation is even a little bit more complicated. In a nutshell, this is because things that are not run by the kernel, so-called userland tasks, cannot preempt kernel tasks. So if the kernel decides it wants to do something, it cannot be, or if the kernel happens to be doing something when a userland process wants to start doing something, it has to wait until the kernel finishes and the CPU becomes available the next time, and that can obviously lead to certain delays for userland processes, and Kubernetes pods are userland processes until that task can be started and finished. On the other side, the kernel can actually interrupt userland processes at any point in time, or almost at any point in time. So the kernel, when a userland process gets the CPU and starts doing its computations, the kernel can actually develop the opinion that it wants to do something anytime, and then the userland process gets preempted and needs to wait until later. Plus, there is a concept that is usually referred to as kernel noise, which basically means the kernel is doing lots of cleanup maintenance tasks sort of in between serving the software that the user is actually running on the system. Things like updating the system time, like managing the scheduler queues and all that kind of stuff. Those are computational operations as well, and they need to be done frequently. Why is Linux designed this way? Why did they do this? The reason is because Linux is optimized for generic compute. Like Linux is a general purpose operating system. It is designed around two major design principles. Number one is fair resource sharing between a large number of concurrent applications, because Linux is essentially a Unix derivative, and Unix was designed in the first place for mainframe applications. So large machine running lots of different things on the same machine. That's where Linux historically comes from. So it is no surprise that Linux is designed around the idea of I need to run many different things, and all these things are supposed to work somehow, and if I run more than the system can eat, then everybody gets a certain share of the CPU. No single process should be able to monopolize the system. Does anyone here in the room have experience with running Windows 95 or Windows 98? So it was not very difficult to actually make the system grind to a halt because of a badly designed userland program, right? There were frequently situations where the system would just freeze, and the only way to unfreeze it was to hit the reset button, right? Why is that? Because those operating systems weren't designed around this principle of resource sharing and kernel being able to always interrupt what the userland does. Right? That's the reason why these systems behave this way, and why Linux and the success of Linux actually comes from the era of Windows 95 and 98. And I personally fell in love with Linux because Linux was always stable. You could not actually sort of render the system unusable and not accessible anymore. There was no way to do that. And that is precisely the reason Linux is designed this way, is precisely the reason for this property. As a side note, there are also a couple of challenges with the Linux with the kernel networking stack, which isn't designed for super high packet I/O. So it is actually also a little bit tricky to saturate line rates beyond 10 gigabits per second with a traditional Linux system that isn't specifically tuned. So you can, of course, it depends on the amount of CPU you have in your system, but actually saturating high-speed links in the ballpark of 25 gigabits and above is actually can become tricky with Linux. So that's another contributing factor why running software run on Linux is challenging. So what are the solutions available to overcome this? To achieve deterministic performance, there are and I'm only singling out a few. There are actually more knobs and levers you can pull and tune. But the most famous or the most well-known ones are the so-called preempt RT patch set. This is also known as the so-called real-time kernel. This is actually a specific modification of the kernel to basically change the behavior of the kernel in certain aspects. For example, to make kernel tasks preemptible or certain kernel tasks preemptible. So what was uninterruptible before now becomes interruptible. It sort of puts the system into a different trade-off between being stable at all times and providing more deterministic performance to userland processes. It is actually a little bit more risky to run a preempt RT system because it is not as rock solid anymore. If you do things wrong, you can actually easier crash it. But if you design everything well, you can actually get a little bit more deterministic performance. There is another feature called CPU isolation. That basically means you can subdivide the number of CPUs in your system or virtual CPUs in your system and sort of make sure that the operating system tasks only run on a certain subset of the CPUs, and then other CPUs can be exclusively reserved for serving your workloads. There are actually kind of two features that go in combination here. The one is CPU isolation, the other one is called full dyntics or no hertz full. And then the last bit is RQ balancing, where you can basically determine which CPUs are used to serve hardware interrupts. And this can remove the so-called kernel noise from a certain subset of your CPUs to a very large extent. And then the last bit that you can use in order to let a Kubernetes application basically run uninterrupted on a certain number of CPUs is CPU pinning. So you can actually tell a userland process, for example, a Kubernetes pod, to only run on certain CPUs. So if you've moved all the noise away from some CPUs, and then you make sure that your process only runs on those CPUs that you've cleared, then you can have basically the full processing capacity allocated to those CPUs. There are a couple of features to address line rate packet I/O as well. that this has mainly to do with avoiding copying packets in memory around unnecessarily. So obviously the packet has to be put into memory when it gets picked up from the network card. But if you do traditional kernel-based networking, the packet actually gets copied a number of times, like from one memory region to another memory region, and that is obviously a somewhat costly operation. With NUMA and huge pages, you can actually avoid that. So the packet basically gets copied into memory once, and then the entire processing chain from the networking driver to whatever needs to process the packet in user land can work on that copy, and the packet doesn't actually have to be copied around anymore. The third bit is hardware acceleration. Things that can be done in hardware don't have to be done in software. You can build specific hardware for certain computational operations. Intel is providing certain acceleration functions which are dedicatedly built to accelerate RAN software. In the third generation Xeons, this is called the ACC 100, which is basically an accelerator for forward error correction algorithms as they are usually used in RAN stacks. In the fourth generation Xeons, which are kind of state of the art today, this has been extended a little bit more, and it has actually turned from a PCIe card into a non-chip accelerator, and is usually referred to as vRAN boost in Intel's marketing messaging. So how do we use all of this in production at scale? Like the at scale part is important, as I said initially, because this complex configuration needs to work reliably in an automated way on a large number of sites. So for each workload, for each cluster, for each instance of the RAN stack, we need to configure BIOS parameters, we need to determine which kernel to use, and with that it determines what the parameters are the kernel needs to be tuned with. We need to set the boot parameters. We need to make sure that we have the right operating system and the right software levels and the right drivers. We need to have the correctly configured Kubernetes stack with additional operators deployed and configured. And of course, we also need to deploy the workload with the manifests and all the required configuration settings. So the $1 million question is, how do I do this, such a complicated configuration, reliably for 10,000 or maybe up to 100,000 of sites? And the answer to that is obviously we need to have very, very robust end-to-end automation from basically unprovisioned cold bare metal. So everything from turning the machine on from the first time to having the workload up and running needs to be fully automated. And then as soon as we get to that state, we need to keep it that way for the entire life cycle, through all the operating system upgrades, through all the Kubernetes version upgrades, through all the workload updates, several years without really with as minimal downtime as possible. The way we do this is by using the principle of GitOps. GitOps is something that has developed a lot of traction in the telco industry lately because it does exactly what I just mentioned on the previous slide. The principle of GitOps is define once and deploy often. So the infrastructure template gets held in the Git repository. It is therefore under version control, so which means that every change to the infrastructure can go through a review process. You can apply the well-known principles of Git to actually manage changes in your infrastructure. You can use peer review, you can run automated checks, you can use even certain CI/CD pipelines on your Git repository. You can make sure that the change, for example, gets deployed into a staging environment first, and if the results obtained from the staging environment are positive, you can actually merge it into the actual main branch from where it then gets rolled out into the actual infrastructure. There is a GitOps engine that basically observes what changes in your Git repository, and it basically makes a synchronized copy in the sense of rsync to your actual infrastructure. So there is a concept here that is called the management cluster or the management server. You have a bunch of Kubernetes applications that are sort of controlling your infrastructure, and the information that sits in your Git repository are basically configuration information for the management cluster. So you copy your deployment manifests to the management cluster. The management cluster runs a couple of controllers which are observing those custom resources, and as soon as they detect a new deployment or a change from the Git repository being synchronized, they will analyze what has changed and will initiate the corresponding change. So for example, picking up a new machine from the inventory and rolling out a new application, running a Kubernetes version upgrade, scaling a cluster up or down, and then times the number of instances that you need. And of course, you can also differentiate your infrastructure in a way that you can group let's say you have like 1,000 clusters running, you can have 300 of those clusters being of type A with a certain configuration on a certain type of hardware, and then you can sort of subdivide your cluster population accordingly, so that at the end of the day you only have to worry about 3 templates that are sitting in your Git repository. You don't have to have configuration for 1,000 clusters in your Git repository. So you never get to see, well, if you want, you can look at it, but you never get to interact with the state definition or the state declaration for every cluster on the edge. So that's the principle of GitOps. With that, I want to come to the use case that we are going to talk about here, because all of this is basically tested and implemented by a piece of software that gets provided by Intel. That is called Intel FlexRun. FlexRun is a reference architecture that basically that Intel is providing to illustrate how to build a 4G and 5G RAN stack based on an Intel platform, making use of all the Intel-specific accelerators that I mentioned before. It assumes an Intel Xeon scalable processor of either, I think, 2nd, 3rd, or 4th generation. And it assumes the hardware accelerators such as vRAN Boost and ACC 100. I've actually earlier today learned that it in principle can run also without those accelerators, but that's obviously what Intel wants to demonstrate with this software in the first place, like how to make use of these accelerators. The nice thing about FlexRun is that it has a built-in test suite for platform validation. So we can not only deploy it and sort of use it to test whether our zero-touch deployment toolchain works, but we can also use it in order to actually validate if the resulting configuration makes the software function according to expectations. And Intel provides reference results for each given version of FlexRun that we can compare our results against, and we will do that towards the end of the presentation so that we can see if our platform works exactly as well as the Intel reference system that sort of they can build themselves. There is actually extensive documentation available for FlexRun, what exactly the tests are and how they exactly work. Just to very briefly explain that there are basically 2 test modes available in FlexRun. One is the so-called timer mode, and the other one is the so-called XRAN mode. The main difference is that the timer mode basically runs both a layer 1 and layer 2 application on the same node, and it's basically sort of simulating a virtualized baseband unit that is deployed like in the same node, whereas the XRAN mode basically simulates the interaction between a virtual baseband unit and an actual radio unit, which means that it kind of assumes a sort of a counterpart that is connected via Ethernet that sort of simulates the radio. We are focusing on the timer mode in the rest of our presentation. And with that, over to you, Alberto.
Okay, thank you. Yeah, so let me change to this one. Okay. Okay, so this part is the demo about what Tim said right now. This is an example on how we are using ATIP in order to use MetalCube KPI, cluster API with an automated workflow in order to, to deploy FlexRun 23 on a 4th generation processors from Intel. So basically the architecture that we have is we have a rancher management component, which is the management cluster that we say usually based on the Intel or whatever server. You can run on top of that the SLI Micro or SLI. Also on top of that we are going to have a K3s or RK2 because it's just dedicated for the management part. So this is only the server that we are using as a management part. And on this demo we are assuming that we are already deployed just to focus on the downstream part, which is the most important part for us. On top of that, we have Rancher Prime, and we have deployed also MetalCube and Cluster API with the RK2 KPI provided that a few minutes ago we saw on the last room. We're going to deploy also inside of the Rancher some kind of plugins with the Grafana in order to have the visibility, the full visibility during the process that we are running on the FlexRun. We have also different kind of tools like cluster, CTL, and logging, and so on. So basically, this is the management part, and what we are going to do is just to deploy a downstream cluster or 8 cluster. that is basically on the hardware for the 4th generation scalable processors from Intel. On top of that, we are going to use the real-time kernel with all features that Tim said before, based on the SLI Micro 5.5. We are going to deploy a single node RQ2 cluster on that part. Let me go back again. During the combustion script, which is the combustion and ignition phase on the first boot, we're going to configure all tools and all requirements that Tim said before related to the telco capabilities like SURV, DPDK, on all configurations that we need to run on top of that a 5G workload. And we are going to use using the combustion script at the beginning of the first boot. So then we will use the SURV device plugin in order to export or to make available the resource to the FlexRun pod. And then at the end of the demo, we are going to use the FlexRun configuration to deploy 2 containers. One of them, as Tim said before, for the L1 application, and the second container based on the FlexRun test Mac. We will run the full test, which take 2 hours, but we are cutting just for the demo purposes, with the timer mode in order to validate that our platform is capable to run 5G workloads on top of that. So let's start with the Metal Cube workflow, because as Tim said, the important thing is just to have an end-to-end workflow without any manual interruption. From scratch until the workload was deployed automatically. So what we have the possibility with Metal Cube is just to having a server which is just only install cable and power on. We are able to enroll this bare metal host into the rancher management part. We are able to create a hardware inspection phase, which basically what doesn't mean is just to get the information from the hardware. We have the possibility to create a cluster, and we are able to install from scratch using an operating system image, which in our case we are using also another tool that we developed, which is the Edge Image Builder, just to install the operating system, the RQ2 cluster, and doing with the combustion script all the configuration to prepare the node to be available for the FlexRun workload on top of that. So let's start with the first part. So basically, we are assuming that we have a bare metal cable, so it's power on, and this is the manifest in order to define a bare metal host. So we have one secret with the username and password, which is the VMC credentials, and also we have a bare metal host that, as you can see, they don't have enough information. So you just have only the information about the VMC URL and just only the book MAC address. So what we are doing is just to creating the manifest in the management cluster, and we are going to start to register into the VMC. What doesn't mean is that we are going to use the credential that I said in the secret, and we are logging to the VMC website in order to start the inspection phase. What doesn't mean is we have a Randex image, which is provided by Metal Cube and Ironic, and we are putting into the virtual media of the bare metal host in order to start a Randex image which run a Python agent. The trick of the magic that we have doing here with this part is that this Python agent is retrieving all the hardware information from the bare metal host, and we will get all the relevant information that we are going to see now. So at the end of this process, when you have the host available, you are able to get all the hardware information, including into the original resource in Kubernetes. So we have information about the Mac, the networking, the hard disks, the CPU model, whatever. All the parameters are included into the object. So this object is now reached, and they have all the information that we need in order to provision the operating system, the RQ2 cluster after that. So once we have the host available, this is a pool available in order to start a provision phase. So what we are going to do is just to define a cluster, which is basically we have the possibility to define the cluster network, and also we will able to use the control plane infrastructure providers from cluster API. We will define the control plane endpoint, and this is the RQ2 control plane part, which means that all the parameters relevant in order to deploy a cluster with RQ2 are defined here. So as you can see, we have the possibility to modify the number of replicas that we have in the cluster, CNI plugin, and we have also the ignition part with the combustion script. This is the most important part that is going to be run the first time that we started the server. So as you can see here, we are configuring the config map with the SURV. So because of the information have been reached with the inspection phase, we are able to configure this part. For sure, we have also the possibility to automate that part using the help charm for the SURV from Rancher, and now in the H repos we have the same help charm. And basically what we are doing is doing the configuration automatically. So as Tim say, on the kernel arguments, we have the possibility to modify the isolation CPU cores, all the telco parameters, or all the telco capabilities. As you can see here, we are able to create BFs using a systemd in order to be started the first time the first boot time. Now we are creating the VS required for the Flex run, and then this is the version for the Kubernetes cluster that we want to deploy, and this is the image we will use, which is based on the H image builder. And the reason of that is because we are doing all the common things for all servers using the H image builder in order to have an image, a foundation, an image basically to be used for all servers, and all the specific things we are able to manage the lifecycle using the KPI workflow. So after applying the manifest, as you can see here, the provisioning step in the bottom tab is starting. And what we are doing here is just to copy the image provided by image builder into the virtual media and attach it into the virtual media and just booting up the server to install the operating system. So as you can see here, with cluster.ctl, we're able to get in during the process the information about the status for the cluster. As now it's installing, we don't have so much information, but after having some time and the host will be provisioned, we will start the configuration and host, and the cluster will be ready. So this is the first boot, as you can see here. After B provisioning, what does it mean is that the operating system has been installed, and the combustion steps will be started. As you can see on the web console, is installing, is registering the operating system into the SUSE support center, installing all the packages required, like DPDK, other kind of packages to run the Flex run on top of that, and everything is automated. So the good thing is that this is a zero-touch provisioning workflow, so we don't need to do nothing, just only defining the manifest. We're able to create from scratch with a blank scratch server till the end, automatically just only defining a web server. So getting access to the host, as you can see, we have a cluster already deployed. The same kernel arguments that we defined into the manifest are applied now. And we have also the CPU configuration for the partitioning with the isolated core that we are going to need for the Flex run application then has been created. And now we have the VFs automatically deployed at the beginning. So we are going, for the Flex run demo, we're going to use one acceleration card resource, which is the ACC 200, 4 VS for the DU, and another 4 ones for the RU. So this is the explanation about the Flex run demo that we have now. And on the left side, we have the L1 application. The right side is the L2 application of maybe the test Mac with the Rapid Sapphire configuration provided by Intel. And in the bottom tab, we will solve the HTOP in order to know which core has been pinned during the test. Also, we have a Grafana dashboard, which we will show the process to deploy FlexRun takes over 2 hours. So with the Grafana, we have the timeline just to have the full vision for the full process. So that's something really interesting in order to, to have the full vision about what is happening, what kind of tests we are running, and which are the difference between one test that Tim said before, changing the CPU, the number of cells, the percentage of the CPU use, and so on. This is the definition for the FlexRun. As you can see, we are using the Intel FlexRun images provided in the Docker Hub, and the resource that we need. So for the L1, we need the accelerator card for the ACC 200. And this is the second container, which is based on the custom Docker entry point in order to adapt what Intel provide to their image into our custom, the custom server that we have different kind of use cores and CPU cores and so on. This is the volume for the use pages that we have and the resources required for the second container. So basically what we are going to do is the timer mode test based on the L1 application on the left side, and the right side will be the L2 with the test Mac and Rapid Sapphire test suite. So now I have to apply the manifest in order to create the timeline timer mode YAML file. And L1 application will start automatically because I have modified the Docker entry point in order to have a loop. He's starting the test. And in the right side, I'm going to start the second container, just putting the logs, just to make it easy to follow the demo. Opening the second container, which is the test Mac part. So just to explain a little bit, what is happening here is FlexRun provide a suite of tests which there are different they are trying to simulate different kind of 5G scenarios. What does it mean is that imagine you want to test different kind of number of cells or the antennas that you have. You want to provide different measures in the antennas that you have. So the FlexRun suite has created different kind of scenario, maybe 80 tests, modifying these kind of parameters. So basically what you are seeing here is that depending on the test, they are saying, okay, we need 80% of the CPU cores for 4 cores isolated just to run the L1 application. And also we need this kind of antennas, this number of cells, and they are creating different kind of, a scenario with all the environments variable that they have, and they are putting just to run the L1 application in order to communicate with the L2. So basically, you will see on these Grafana graphics that depending on the test, the number of core spins are different, the percentage of use CPU are different, and it's because they were trying to validate your platform in order to say, okay, your platform is capable to run 5G workload because the number of the scenarios that we are testing and we are validating are 80, and you are passing all the tests. This is more or less the idea of this kind of test, and as Tim said before, the important part here is that without so many fine-tuning features related to the isolated real-time kernel and so on, we are able to pass all the tests, as you are going to see now. The performance results after this test, Intel provides you performance results, which is comparable with the Intel results that they have provided in the official site. And the idea of this test is just to compare the percentage of difference between your values and the Intel ones. It's not a competition. I mean, it's not only just to say, okay, my values are better or not. It's just to have your values are inside of the margins acceptable by the Intel because they say that your platform is capable to run this kind of 5G workloads. So after that, after sometimes it takes over 2 hours, and at the end of this test, I think we will have here, as you can see, 79 of 79 passed. So what does it mean is that we are able to run all the tests that they are providing the FlexRAN. And this is how it looks related to the CPU cores utilization. So I think the values that we are getting, now we are going to have the result that I think Tim has more knowledge than me to explain that. But the idea of that is just to compare the percentage of the difference between our values and the Intel ones. And inside of this graph, you can see that the values, most of that, are inside of the acceptable values and acceptable margins that Intel provide in their suite. Tim?
Yeah, so
do
maybe
you want
one
to
final...
add something about the results?
I mean, the interpretation of the results is really simple. There is a certain amount of randomness in this because the isolation of the CPUs is relatively far-reaching, but not totally complete. So there are still a few operating system tasks that are running on the isolated core. So when we run these tests a number of times subsequently, we always see slight variations in the results. And we have actually shown the results from only one run, so we haven't actually averaged over multiple runs here. But what we can see, and we have actually discussed those results with the Intel team, is that we are within the to-be-expected variations, which can be taken as a proof that our system is designed correctly according to what Intel see in their own evaluations and what they think is an achievable performance given the platform that we are using. If we look at what kind of results we have, let me actually fast forward to this slide here. I think let's take this one. So what we're basically getting here is, so you see that all these results are basically expressed as percentage, and the percentage basically means what is the relative performance we see for the given metric compared to the performance from the Intel, to the number from the Intel performance report that comes with the relevant release of FlexRAN. I think we're using FlexRAN 23.11, right? So there is a performance report that you can download from the Intel website for exactly that FlexRAN version, and you get the numbers that you can compare against from that report. Fortunately, they're providing Excel sheets as well, so we didn't have to actually type all the numbers into our own sheets. And they have a tool which can generate the performance reports for us, so it's a really nice and easy process. So what can we see here? We can see that basically, I mean, I want to focus on the two left bar groups first. This is basically the number of logical cores that are used to execute the test. So this is basically a metric for the computational efficiency of the overall application. And you can see that, and the different scenarios, you can see the legend at the top is basically for different cell configurations. So there we run one 20 megahertz carrier with a 4x4 MIMO configuration. We run a 100 megahertz carrier with an 8x8 MIMO configuration. We run a 10 megahertz carrier, another 20 megahertz carrier in a slightly different configuration. I don't actually know right now off the top of my head what the light blue and the slightly darker blue really where that differs, but those are actually documented in the FlexRAN documentation, and you can look it up there. So the average number of CPU cores utilized is basically a measure for how efficient we are, and you can see that there is a slight tendency to be a little bit more efficient than the Intel platform. The Intel reference results have been obtained using Ubuntu, so you can sort of take this as an indication that our operating system performs a tiny little bit better than the canonical one. We have throughput numbers for the packet downlink shared channel and the packet uplink shared channel. Those are like the two right-hand side graphs. And there you can see that we're actually deviating in both directions a little bit. So some results are better, some results are worse, but still within the margin of error that, according to our friends at Intel, that is to be expected given the slight randomness of the compute environment. And that's actually where I want to leave it. I'm not sure how we're doing time-wise. Do we have time for questions?
We do, I think. I was going to say that I'm pretty sure the difference between those two 20 megahertz carriers is FTD versus TDD.
Yeah, that's entirely likely.
Before we take questions, I was also going to, it occurred to me having put this together and then sort of watched through now, one of the things worth saying actually about real-time as well is we talk about all the requirements on the software side, but it also requires a great deal of validation on individual hardware. We do see some models for server just down to like the BIOS configuration or something that you will never get acceptable real-time performance from that hardware. So that's another part of the work we do is validating that in our lab, that we can achieve that configuration and those numbers on specific models of hardware. So this was done on Dell XR11s.
No, those results are from the Supermicro
these
machines,
Supermicro
I think.
boxes. Yeah. So, but it's worth saying that it is an important element of this. There are some boxes which you're never going to get to reliable real-time levels of performance on, just because of the architecture of the systems themselves. Things like BMCs and such are effectively stealing clock cycles in some of the architectures, particularly on lower-end boxes. So another interesting and challenging piece of getting this working to a standard where it works, produces the results we need, but then also that we can do it at scale, that we can do this 1,000 times. Obviously, all the sort of manifests and artifacts you see here, we'd expect in production that you'd be mutating those files in an automated way using your GitOps process to drive that out to several thousand machines if necessary. But with that, I think I can stop talking, and if anybody's got any questions, then I'll pass the mic along.
It's okay.
I want to get it for the recording more than anything.
Yeah, just I think it's about slide number 5 when you were talking about kernel settings, real time or CPU affinity or pinning. If you have 10,000 nodes, for instance, how do you choose one of these, or can you use them? Can you set this kernel parameter separately for let's say 3,000 nodes and the rest of 7,000 nodes? So you put, for instance, CPU isolation for some of them and CPU pinning for others.
So we can, so there's a couple of things that are at play here, right? So number one is on the actual management cluster, every machine is represented by a infrastructure declaration. So like every machine has its counterpart of declared state or desired state on the management cluster. The one-to-many mapping happens on the way from the Git repository to the management cluster. That is where the template rendering happens. So let's imagine you have two different types of machines in your infrastructure, and you want to configure them slightly differently. There are maybe the threat model of your application is different, therefore you need to pin different processes to different CPUs. You will have two different templates in your Git repository for that configuration, and that configuration will then be equal across all the machines that belong to a certain type. And then you will have some form of information source that basically provides you with the information on how you need to mutate your template. Like, for example, every node gets an IP address from a given subnet. Then you will have in your manifest, you will basically specify like a placeholder for this is the IP address, and then you will instruct your GitOps engine to instruct to basically assign an IP address from that subnet in the process of sort of taking the resource from the Git repository down to the cluster. And the resource that gets deployed on the management cluster itself will then have the final IP address in it. And that is then how it gets propagated to the actual machine. And you can take that as an example of basically any kind of configuration that can be mutated. And there are various ways you can interface with an additional information source. You can, for example, put that information source in your Git repository as well. So you can basically point to, this is my template, and here's my list of IP addresses that are supposed to be used for all instances of that template. But you can also point to, for example, an external database, an element management system, or something like that, where in real use cases, this information is often to be found. And of course, there are also inspection loops possible in the sense of, during the inspection phase that Alberto has shown, the machine can basically sort of investigate its environment, provide some information back to the management cluster, and then we can apply some logic as to how to derive the final configuration based on the inspection information. So that's also possible to script.
Anyone else?
It's the last presentation, right?
I was going to say, well done for getting to this point in the week, everyone. I know these events are hard. But I guess unless there's anything from anyone else, then I guess from the SUSE Telco team, well, thank you for attending SUSECon. I'd encourage everyone to try and make it to the Demopalooza. Apparently there's going to be fun and interesting stuff. shown there. So, including, I think there is going to be a demo of the stack state solution
interesting.
as part of
I wanna
that.
see that.
So, I would encourage everyone to.
Thank you, guys.